നമസ്കാരം. കഴിഞ്ഞ ഏതാനും ദിവസങ്ങളായിട്ട് നമുക്ക് ക്ലാസ്സുകളൊന്നും ഉണ്ടായിട്ടുണ്ടായിരുന്നില്ല. Hopefully we begin today. As far as I'm aware, നമുക്ക് ഫസ്റ്റ് മൊഡ്യൂളിൽ 2 തിയറങ്ങൾ ബാക്കി കിടക്കുന്നുണ്ട്. 2 പ്രധാനപ്പെട്ട തിയറങ്ങളാണ്. ഒന്ന് യൂറിസൺസ് ലെമ്മയാണ്. മറ്റൊന്ന് റേസ് റിപ്രസെന്റേഷൻ തിയറമാണ്. ഇത് രണ്ടും വളരെ പ്രധാനപ്പെട്ട 2 തിയറങ്ങളാണ്. നമ്മുടെ കോഴ്സിലെയും ഹോൾ തിയറി ഓഫ് മെഷറിലെയും ഒക്കെ മാത്തമാറ്റിക്സ് തന്നെ കൺസിഡർ ടു ബി മേജർ തിയറംസ്. അപ്പോ ഫോർ ദ സേക്ക് ഓഫ് ടൈം നമ്മളിപ്പോൾ ഇതിന്റെ രണ്ടിന്റെയും പ്രൂഫ് ഡിസ്കസ് ചെയ്യുന്നില്ല. വിൽ കം ബാക്ക് ടു ദിസ് ലേറ്റർ. സോ നമുക്ക് ഇതിന്റെ രണ്ടിന്റെയും സ്റ്റേറ്റ്മെന്റ്സ് ഫർദർ അനാലിസിസിന് ആവശ്യമാണ്. സോ വിൽ വിസിറ്റ് ദ സ്റ്റേറ്റ്മെന്റ്സ് നൗ ആൻഡ് let's move towards second module. Okay. So നമുക്ക് ഇവയുടെ സ്റ്റേറ്റ്മെന്റ്സ് ഒന്ന് പരിചയപ്പെടാം. So Urysohn's lemma, before proceeding to Urysohn's lemma, I want to remind you a notation which you might be familiar with. Right. So you might have seen this notation in this course itself. So what does this mean? Suppose K is a compact set. K is chosen to be compact set in our whole course, and this notation means where f is a function and f is not any function. F is considered to be from CCX. You remember this notation, right? CCX means the set of all those functions from X with a compact support, right? So this notation means K is a compact subset of X. K is a compact subset of X, and F belongs to CCX. That 0 less than or equal to f of x less than or equal to 1 for every x in X, for every x in capital X, such that f of x equal to 1 for every x in A. Right. So this notation means K is a compact subset of X and f is an element of CCX, which means a function with a compact support on X, and the value of the function is in between 0 and 1 for every x in capital X, and f of x equal to 1 for every x in K. Right. So sometimes in our analysis this may get the significant role of a characteristic function somewhere or something close to the characteristic function. Right. So in any sense this can sometimes distinguish the set K using F. Right. We have a similar notation but with a slight change in meaning. That right. So this notation means the set V is open in X. Obviously, we define and we discuss everything on X. So V is open, and as we have seen, F is in CC of X, and 0 less than or equal to f less than or f of x less than or equal to 1 for every x in X, and the support of V and the support of the support of f lies in V. Right. So you know what is the support of a function, and obviously it's a set, and that set lies inside of V. So this notation means V is an open set in X, f is from CCX, and the value of f lies in between 0 and 1 for any x in X. Moreover, the support of f is in V. The support of f is in V. Right. So I hope you remember these two, and these two notations or these two concepts may come jointly as this. So this is a kind of relation. This means the both concepts we have explained a little ago comes together. Right. So K is a compact set, V is an open set. F is such that, from this expression, F is such that F is from CCX. The value of F lies between 0 and 1. And the value of F is identically 1 for K. And the support of F lies in V. Right. Okay, so now let's go to Eurosum's lemma. See, the statement of Eurosum's lemma seems shorter and simpler, but the implications are not so. Eurosum's lemma has got wide ranges of application. Right. So, let X to be a locally compact host of space. Locally compact host of space. I hope you remember what do we mean by locally compact and host of. Alright, they are from the fundamentals. Let V be an open set in X. V subset of X is open. V subset of X is open. Also K be a compact subset. See like this. This is the standard notation. So it K be a compact set. Then there exists a function f. There exists a function f in CCX. There exists a function f in CCX such that K is related to F is related to V, as we have defined a little ago. Right. So this is what Eurosum's lemma assures. Eurosum's lemma assures the existence of such a function f for any choice of open set V and a compact set K, and see, X has to be locally compact here and host of. Right. So under these assumptions, we have a function f with this expression stands satisfied. Right. So this is about Eurosum's lemma. Or this can be slightly rearranged or paraphrased to express Eurosum's lemma in terms of characteristic functions for K and V, as Eurosum's lemma asserts the existence of a continuous function f such that chi k is less than or equal to f, which is less than or equal to chi v, where chi k and chi v are the characteristic functions of compact set K and the open set V. So that's about the Eurosum's lemma, and that's the statement, and we don't visit the proof for now. And then comes the star. Rees representation theorem. Right. The statement as well as the proof of Rees representation theorem is kind of large. Large in the sense it's very, very huge. Right. This spans over several pages in your textbooks, and yeah, let's see, we'll prove it somehow, or whatever, we'll prove it. And for now, let's see the definition or the statement of the theorem. We may use these theorems several times in our due course. So, as we have seen for Eurosum's lemma, let X be a locally compact host of space. A locally compact host of space, and let lambda, this is capital lambda, be a positive linear functional on CCX. Positive linear functional on CCX. Right. I hope you all have textbooks. You may refer the theorem from your textbook whenever you come up with a doubt. Right. Or you may take notes and suffer. I have a restriction that I cannot write the whole theorem over my small board, so I'm supposed to write the major points. Right. So let the setup be like this, and let M be a sigma algebra on X, which contains, this is not just any sigma algebra, but this sigma algebra contains all the Borel sets. So I hope you remember the Borel sets. It's come from the part of topology where you construct is the collection of all those sets which you can be constructed from open sets, closed sets by the operations of union, intersection, or complementation. Right. So this set, this sigma algebra M contains all those Borel sets of X. Okay. So there is an underlying topological structure to be assumed on X, and that's where this Hausdorff and all comes from. Right. So from the same topological structure assumed to be on X, we assume that the sigma algebra M on X contains all the Borel sets. If it is a set, if it is the case, there exists a unique positive measure. So there exists, here comes the conclusion. There exists a unique positive measure mu on the sigma algebra M, which we just constructed on M, which represents lambda, which represents the positive functional lambda in the sense lambda of f is equal to integral over x f d mu for every f belongs to CCX, right? Since lambda is an operator on CCX. So this is what Rees representation theorem tells us, that the positive linear functional lambda defined on the set of all functions on X with a compact support can be represented using a measure mu, in the sense that lambda of f is equal to integral over x f d mu. Right. That mu comes from the sigma algebra M, which contains all the Borel sets. Moreover, this representation has some additional properties which is also ensured by the Rees representation theorem, and they are that measure of k is finite for every compact k. See, Rees representation theorem assures the presence of such a measure, or the existence of such a measure, with which we can easily represent the linear functional or any positive linear functional lambda, and such a measure will have a few more additional properties, and we are trying to list them out. So for now, the measure of any compact set will be finite, right? Moreover, for any measurable set E, or for any set in the sigma algebra, the sets in the sigma algebra are called measurable sets. In sigma algebra, we have measure of E to be the infimum of measure of V, such that E is contained in V and V is open. Measure of E can be identified as the infimum of a set, and that set is the collection of all measures of all those open sets in which E is contained. You might have seen this, and this is sometimes referred as the outer regularity. Right, outer regularity of the measure, of this particular measure, and we will name this measure soon, and that's a familiar name. We'll come to that. So this is a property to be held by this measure. This measure can be identified as the infimum of all those measures of open sets in which the set E is contained. And there is an alternative property for this, and that is, see, if we have called this as the outer regularity, we hopefully expect something to be inner regular as well. So this measure of E can also be expressed as the supremum of all those measures of those sets which are contained in E and are compact. So this measure can also be expressed or also be identified as the supremum of the measures of all those compact sets which are lying inside or which are sitting inside the required set E. Right. So this may be sometimes referred as the inner regularity property. Alright, so these two are considered to be two major properties of this measure, and we will be using these two properties sooner in our further analysis. Okay. Also, for any measurable set E, which is in the sigma algebra, and A is any set inside E, and measure of E is 0, then A is in the sigma algebra. This property talks about the subsets of sets of measure 0. The subsets of sets of measure 0. Like E is a measurable set and which has measure 0, and A to be any subset of E, then A has to be a part of the sigma algebra. That was all about Rees representation theorem, and now let's move to the second module of our course, which starts with the regularity properties of Borel measures. So we have seen these two expressions for the measure mu, which we have defined and which is ensured by the Rees representation theorem. This is a measure of E can also be identified as the infimum of measures of all those open sets in which E is contained, and the same measure of E can also be identified as the supremum of all those compact sets which is contained inside E. Right. These two properties, as we have discussed a little ago, are called the outer regularity and inner regularity of measure. Right. So this property is called the outer regularity, which in the sense we are trying to shrink down the measures, or we come closer to the set E from the outside through the open sets. Right. And this is called the inner regularity, in which we try to approximate the set, or we try to move towards the set E from inside the set E itself through the compact sets. Right. So remember these names, inner regularity and outer regularity, and if a measure mu has both of these two properties together, if a measure mu has both of these two properties together, such a measure may be called a regular measure. Right. A regular measure. A regular measure. Alright. So what is a regular measure? A measure which is both outer regular and inner regular. And we now know what we mean by inner regularity and outer regularity. Right. So let's move on. And we have a few more definitions to be discussed before moving to the analysis part. So hope you remember sigma compactness from your topology courses which you have done so far. Right. So sigma compactness, we'll just define it. A set E in a topological space. So if you want, you can choose X to be a topological space, and E to be a subset of X. Right, whatever. A set E in a topological space is said to be sigma compact if E can be expressed as a countable union of compact sets. Right. So a set in a topological space is said to be sigma compact if it can be expressed as a countable union of compact sets. Right. We have a similar definition with measures. See, throughout the course of measure theory, you might be identifying certain similarities with measure theory and topology. Right, we have topological space, we have measurable spaces here. We have open sets, we have measurable sets. Right, we have a topology and we have sigma algebra here. And there are a lot of similarities with these two theories of measure and topology, and the analysis, for that reason the analysis seems similar. Right, so like sigma compactness, we have sigma finiteness, which comes from the measure part. So a set E in a measure space, you remember the definitions of measure space, measurable space and everything, right? Which it might be discussed in your course so far. So a set E in a measure space, say X to be a measure space with measure mu, right? Is said to be sigma finite, or is said to have a sigma finite measure. So E in a measure space is said to have a sigma finite measure, or simply E to be sigma finite if E can be expressed as a countable union of sets with a finite measure. If E can be expressed as a countable union of sets with finite measure. See, I belongs to the indexing set I, where I is countable. Right, so this represents a countable union. So let's recollect. Sigma finiteness means if E is a set in a measure space, then E is said to be a set of sigma finite measure, or E is said to have a sigma finite measure, or simply E is a sigma finite set if E can be expressed as a countable union of sets of finite measures. So remembering these definitions, now let's start our analysis with the theorem. So I repeat that you may get ready with your textbooks, or you may take notes. It's impossible to write the whole theorem over the board. So we will be writing or emphasizing the major points, and we will be we'll be clearing of that very soon. So suppose the theorem is, suppose X is a locally compact, sigma compact host of space. So X is locally compact, sigma compact, and host of, right, as a topological space. If the sigma algebra M, and the measure mu are as defined in the statement of Rees representation theorem. We have just seen the Rees representation theorem, in which we defined the measure space M to be the measure space which contains all those Borel sets, and the measure mu was defined as mu represents the positive linear functional, that capital lambda, as capital lambda of f of x equal to integral f of x mu d mu, right, integral over x f d mu. So this M and mu are as defined in the Rees representation theorem. Then the measure and the sigma algebra, or the sigma algebra and the measure, will satisfy a few more properties, which are if E is in the sigma algebra, or in other words, if E is a measurable set and epsilon positive to be any given number, however small it is, then there is a closed set F. There exists closed set F and open set V. There exists a closed set F and an open set V such that F is contained in E, which is contained in V, and the measure of V minus F is less than epsilon. right? So if E is any measurable set in the sigma algebra M, and epsilon to be any given number, then we can find two sets. One is closed and which sits inside E, and the other one is an open set in which E sits, right? And the measure of the difference of those sets, measure of V minus F, and this is actually the set difference. See, this is actually the set difference V minus F, and just following the notations in your textbook, routine likes this notation. So V minus F, and the measure of that set is less than epsilon. See, less than any positive number epsilon, which just means it goes to 0, right? See, measure of a set is 0 doesn't mean that the set is empty. Remember that the measure of the set 0 does not mean that the set is empty, right? Okay, so that's the first property. We can find two sets with this specialty. And the second property is mu is a regular measure or a regular Borel measure, right? In fact, this can easily be deduced from the previous property, the first A part. We'll come to that. Okay, and the third property, C. If E is any measurable space, then there exist sets A and B. We were discussing about open sets and closed sets so far. So now these two sets A and B are such that A is F sigma and B is G delta. I hope you remember what are F sigmas and G deltas. F sigmas are those sets which are unions of closed sets, and G deltas are those sets which are intersection of open sets. Right. So A is F sigma and B is a G delta set, with the property that A is contained in E is contained in B, and measure of B minus A is 0. Right. Again, this can be deduced from the first property A part. We'll see that. So let's move to the proof. So the proof. So what do we have from our theorem? So we have an information that X is sigma compact, which means X can be expressed as a countable union of compact sets. So choose X to be some K1 union, K2 union, etc. union, Kn. See, this need not be finite, right? We just need to be countable. So X equal to K1 union, K2 union, etc. union, Kn, union, etc. where each Kn is compact. Where each Kn is compact. If E is any measurable set, or let E be an element of the sigma algebra M, and epsilon to be positive, be arbitrary, then measure of Kn intersection E is finite. See, there is an intuitive reason behind this. The measure mu is actually comes from, from the statement of this theorem. Mu is actually as defined as in the Rees representation theorem, and in the statement of Rees representation theorem we made a remark that the measure of compact sets has to be finite, right? So Kn intersection is anyway going to be a subset of Kn, right? Kn is a compact set, so this is somehow going to be a subset of a compact set, and the measure of a compact set itself is finite, so the subset of such a set with a finite measure has to be finite, right? So for that reason the measure of Kn intersection E has to be finite for any n. Okay. Then there are open sets. Vn, which contains Kn intersection E, such that measure of Vn minus Kn intersection E is less than epsilon by 2 raised to n plus 1, where n is in the set of all natural numbers. What does this mean? If it is the case, we can find open sets in which the set Kn intersection E contains, and the measure of the difference between these two sets is getting smaller and smaller. Or to be a little more easier, we can find open sets which can be used to approximate the set Kn intersection E, and this is a significant implication of the outer regularity. Right. And I forgot something. When we discussed about outer regularity and inner regularity, outer regularity is actually which can be easily proven using Rees representation theorem, and which is expressed in the large proof of Rees representation theorem. We will see it sooner. So for now, remember that the outer regularity is kind of obvious thing, right? Which comes from the definition itself, but inner regularity need not be always that obvious. We will see the reason soon, right? So there is something playing between playing with inner regularity, and to prove a measure is regular, in fact we need to prove both outer measure, it's outer regular and inner regular. But in almost all cases, outer regularity comes trivially obvious, and we may just need to prove the inner regularity part only. But in this case, as we see here, this expression comes actually from the triviality of outer measure. Okay, so the difference between the measure of the difference between these two sets comes closer to 0 means they each can be used to approximate. The Vn's can be used to approximate the measure of Kn intersection E. Right. So now we make a construction. Let V to be the union of all those Vn's. See, each Vn corresponds to each Kn. Right. So let V to be the union, capital V to be the union of all those Vn's. Then V minus E. See, these are all the set differences. Remember, these are not just negative sign or minus. These are the set differences. So Vn minus E is a subset of Vn minus or union of is a subset of union of Vn minus Kn intersection E. You can visualize this. See, V is the set of all, the union of all these Vn's. So V minus E has to be somewhere inside the union of all Vn minus Kn minus E's. And for a better visualization, you may use a Venn diagram with the 2 or 3 sets, or n equal to 1, 2, 3. Right. So which can easily be visualized. And moreover, we have measure of V minus E is less than epsilon by 2. This comes from the fact that the measure of Vn minus Kn intersection E is less than epsilon by 2 raised to n plus 1 for every n. Right. So you know how does the additivity works here. And see, epsilon by 2 raised to n plus 1, and this is the largest possible one. So the measure of V minus E and V minus E being inside the union has to be less than epsilon by 2, somewhere less than epsilon by 2. Now, apply this idea to E complement instead of E. What were our assumption on E? E was assumed to be any measurable set, right? So from the definition of sigma algebra, if E is an element of the sigma algebra M, then E complement has to be an element of the same sigma algebra, right? So whatever applicable to E, which can also be applied to E complement as measurable sets. Right, so now let's apply this statement for E complement. So there exist open sets W. For E we had V, so we just change the name here. So for E complement there exists open set W, which contains E complement, and measure of W minus E complement is less than epsilon by 2. Right. So this is what we have from our analysis. Now choose F to be W complement. See, if you want, you can try to visualize this as say, let this to be the universal set and let this be our E. W contains E complement. So these are all parts of W, and we choose F to be W complement. So obviously E will be somewhere inside, right? Or sorry, these are the parts of E complement, and these are parts of W, and F is assumed to be E complement, F is assumed to be the W complement, so F must be somewhere inside E, right? So somewhere inside E, so let's note it down. F has to be somewhere inside E, and these things can be easily verified using a Venn diagram. I suggest you to try them out. So, and E minus F is nothing but W minus E complement, right? So this can also be verified easily with a Venn diagram, a simple Venn diagram. We have only 2 or 3 sets here, and so what does we have now? Remember, we have measure of W minus E complement. W minus E complement is less than epsilon by 2, and E minus F is nothing but W minus E complement. So measure of E minus F is less than epsilon by 2, right? So we had open sets V such that measure of V minus E less than epsilon by 2, and now we have closed sets F. See, why F is closed? That's an obvious reason for that. See, W was assumed to be an open set containing E complement, and then if W is an open set, W complement has to be closed, right? So for that reason, F is a closed set. So combining these two, we will get the first part, the A part, right? We got 2 sets, V and F. V is open and F is closed, and you can use the additivity property, right? To claim that, you can use the additivity property to claim that measure of V minus F is less than epsilon, right? Which we were actually wanted to prove. Okay, so that's how the proof of first part works. Now we may use the first part to prove the rest. So the second part is mu is regular Borel measure on M. So to prove the regularity, we assume it's outer regular by triviality. We'll see why is it trivially outer regular. We'll see. For now, believe that. And now we need to show that mu is inner regular, or every set can be expressed. I mean that expression for inner regularity. So measure of E can be expressed as supremum of all those closed sets. Measure of closed sets. So I use F here. All those closed sets such that F is contained inside E, and F is compact, or not just closed sets but compact sets. So this is how we defined the inner regularity. And we have an expression, measure of E minus F is less than epsilon by 2 here. We may make use of this. So now choose, let F subset of X be closed. We will go this way. Let F subset of X be closed. The first question is F sigma compact? Is F sigma compact? Obviously, since F can be expressed as F intersection Kn. Right. So each of this will be compact. Since F is a closed set and Kns are compact by definition. So F can be identified as a it's the union of F intersection Kn. So F can be identified as a sigma compact set. So if F is closed, then F is sigma compact. From the first part, we have an idea that we had a set, or we had sets F which was contained in E, or we had F contained in E, and measure of E minus F was actually less than epsilon, right? So this means that we have sets inside C, we have closed sets inside E. Closed sets are nothing but sigma compact sets. So this means we have sigma compact maybe just compact or sigma compact sets inside E, which can be used to approximate the measure, right? Which is actually we wanted to prove. See, this expression says the same. We have compact sets inside C, which can be used to approximate the measure E if from inside the set E. Right, the same is meant here. We have sets inside E, which comes closer to the measure. The difference of the measure of their difference comes closer, which means those two sets come arbitrarily closer. Right. Remember, the measure going to be 0 never means that those two sets, those set is going to be empty. Okay, so by that statement, we can conclude that the measure mu is inner regular, and since we assume trivially that the measure is outer regular, we can conclude that the measure is regular, and the second part is to prove mu is a regular Borel measure, and it's obviously a Borel measure since the sigma algebra M is by default containing all the Borel sets. Right. So it's a Borel set. Now the third part. In the third part, we were supposed to find two sets A and B. A has to be an F sigma and B has to be a G delta. Right. Such that A is contained in E is contained in B, and measure of B minus A is less than epsilon, or going to be 0, or it is given as just 0. See, less than epsilon for every epsilon or equal to 0 does make a significant difference. Okay, so we need to construct those two sets. We have a similar expression using E and F, but E and F need not be F sigma and G delta. For to find F sigma and G delta sets A and B, we make a small construction here. Choose epsilon to be say 1 by J, where J is any natural number. Okay. Now for this epsilon, we can find closed sets Fj's and open sets Vj's. Right. We have seen that for any epsilon positive, we have F and V, such that measure of V minus F is less than epsilon. So for epsilon equal to 1 by J, we can find Fj's and Vj's such that E is contained in between them, or Fj is contained in E, which is contained in Vj, and measure of Vj minus Fj is less than epsilon, and epsilon is 1 by J here, which is less than 1 by J. So this is possible, right? So such a construction makes sense. So we can find Fj's and Vj's such that measure of Vj minus Fj is less than 1 by J. Right. Now choose A to be union of Fj's and B to be the intersection of Vj's. Then obviously A is an F sigma, since A is a union of closed sets, and B is now obviously G delta, since G is an intersection of open sets. Right. Also, and this remember these EIs and these VIs and FIs and VIs are defined such that Fj contained in E contained in Vj for any J. Right. Then since A is equal to union of Fj and B is equal to the intersection of Vj, we can conclude that A is contained in E. Since every Fj is contained in C, so their union has to be in E. Every Fj is contained in E, so their union has to be in E. And E is contained in every Vj, and for that reason E has to be in the intersection of all the Vj's, so which is B. Also, right. Okay. Moreover. So we got the first part, and now we need to prove that measure of B minus A is 0. Right. Now B minus A is contained in Vj minus Fj for every J. You can visualize this, since B is the intersection of all Vj's and A is the union of all Fj's. B minus A has to be strictly contained inside Vj minus Fj. And measure of Vj minus Fj is less than 1 by J. So if something is less than 1 by J for every J, so the measure of B minus A, we have the property of measures. If A is contained in B, then measure of A will be less than or equal to measure of B. So if B minus A is contained in Vj minus Fj for every J, measure of B minus A will be less than or equal to measure of Vj minus Fj for every J, and the measure of Vj minus Fj is less than 1 by J. So the measure of B minus A is less than 1 by J for every J, and this means measure of B minus A is 0. Right. So J is less than 1 by J for every J. Right. So that completes the third part as well. So this completes the proof of the